So first, couple of warnings. I have a bit of a cold, so hopefully we can get through this without too much sneezing. And also, this is about Android security architecture. There's nothing groundbreaking here. It's probably stuff you already know if you're doing research. Hopefully, there is a couple of new things introduced in the newest version, which I've tried to incorporate, but this is mostly basic stuff, and there's also a lot of it, so hopefully we have enough time. So the basic things I'm going to try to cover is Android's architecture, security model, of course, how package management works, applications, and how they're installed, permissions. Of course, everybody's talking about permissions because there's been big changes in the upcoming 6.2 release. SE Linux, which is also a kind of a new, relatively new addition to the Android security model. User management is been something which has been around for a while, but kind of overlooked, but it got a big facelift in Android 5, so I'm trying to cover that as well. Also briefly about cryptography, PKI, credential storage. Those are very, very broad topics, but I'll just try to cover the basics. Enterprise security and Android for work. Those are things which were introduced in the 5.0 release, I believe. A lot of changes there. Hopefully we can cover the basic stuff. Device security and verified boot. This is been a lot of work going in this area, but it's been mostly behind the scenes. And we finally have some, official documentation about it. So it's also a very exciting topic, but also very extensive. So hopefully we can get through the basics. And finally, NFC secure elements, which is not really part of the core security architecture, but it's important because it covers how you can access secure elements, which is something very, very interesting research topic and also an important topic for our hosts. So first, Android's architecture is a variant of this diagram you've probably already seen. Maybe everyone has it slightly different. Starting from the bottom up, of course, we have the Linux kernel. Android is based on Linux, and most of the security measures and app isolation is based on Linux. But of course, once you start going up the stack, it gets very different for a traditional Linux server or embedded device. On top of it, on top of the kernel, you have native services, starting, of course, with init, which is, again, very different from the init you see on desktop or embedded devices. You have, of course, native daemons, native libraries, the hardware abstraction layer, which is kind of the glue between the kernel and the Android services. On top of that is the Android runtime, originally Dalvik, now it's ARP. And from there up is actually the core of Android, which is a whole number of system services which cooperate together. And I guess you could say that, Android service is a kind of big build and object-oriented system on top of the Android kernel. And of course, on top of that, the Android framework libraries, which applications used to communicate with the layers below. And of course, at the very top is applications. There's this division between user-installed application and system applications, because system applications have traditionally been given, more privileges, mostly because they are on the system partition, therefore they can be trusted. This has been changing lately, maybe starting with 4.4. Maybe we should now talk, instead of system application, about privileged applications, because system applications are not equal nowadays. We have system applications which live on the system, partition, but not really highly privileged, and also privileged applications which can get extra permissions. So this is the basic architecture, but of course on a modern device it looks more like this. On one side you have the Android OS, which is what we talked about, and there is also additional secure OS or trusted OS, which is sometimes called, which is completely different. It is isolated from the main OS, so the idea, of course, being that even if the main OS gets compromised, what is stored in the secure OS or the services the secure OS provides, they remain secure. There's different ways to implement it. You can be on a dedicated chip, it could be virtualization, but on most ARM devices, it's based on trust zone, which is an ARM feature which allows code running on the same hardware to switch between a normal world and a so-called secure world. Also, the memory is isolated, so the normal world, what is stored in the normal world's memory and what is stored in the secure world's memory are separate. And the normal world, there is no way to directly access what is in the secure world. What this secure OS or trusted OS is mostly used for, traditionally it has been DRM, and since the last few versions we also have key store, which is basically a secure storage for keys, and there is an official API accessible to application, which we'll cover in a while. And of course, this being a secure OS, it is still basically a bunch of C code, and there have been, and probably there will be other vulnerabilities and ways to export it. Hopefully we'll hear more about it tomorrow from both sides. And again, this particular diagram is taken from the Android for Work security white paper, which, even though it says Android for Work, is a nice introduction to Android's security model and architecture, so you should definitely look at it if you haven't. So based on this, what are the basic points of Android security model? We have the application sandbox, which is again based on the kernel. It is implemented by using traditionally separate user IDs and group IDs to isolate applications and their data, which is, of course, the Linux's discretionary access control. And it has been augmented recently, starting since 4.4, with SE Linux mandatory access policy-based control based on SE Linux type enforcement. Of course, those applications are isolated, but they wouldn't be particularly useful if they were completely isolated from each other. So you have secure IPC. Different ways to communicate between applications and processes are also integrate some security features. The easiest, probably the basic one is using local sockets or Unix domain sockets. And of course we have Binder, which is probably one of the central features of Android that sets it apart from other Linux-based systems. And of course intents for communication between applications, they also have incorporate some security features in there. As we saw in the first slide, there is a lot of native code below all of the framework and the system services. Android has been evolving in the direction of trying to drop all the privileges which are not strictly needed. So most of the native services, they try to use Unix capabilities, Linux capabilities, and drop all the capabilities which they are not needing. Of course, we have code signing. Code signing here is quite different from what we have, let's say, on iOS, where you cannot execute any code if it's been signed. There is no code sizing for native code per se. It's only for application packages and OS updates. We'll look into detail in a bit. Of course, Android permissions. We have system and custom permissions which are required to access anything from system resources, hardware, to personal information, and of course, application components from other applications. So starting on with Binder. Binder is an IPC which is based in the kernel. It's very core. It's actually quite small, but still multi-feature. It provides different services. You can read through it if you're interested. It's probably a good exercise. But what is important here that when you have two processes which are communicated, the communication goes through the kernel. So there is, barring any vulnerabilities or errors, there is no way for a process A to fake its identity and try to get a higher privilege than it has, because the process identity, the process ID, and effective user ID, they are filled out by the Binder driver. So as long as you can trust the kernel, you can be pretty sure that Binder IPC is secure. Another important aspect of how the sandbox is implemented is how packages are installed. So if we look at it in a bit more detail, we have an Android package. APK file is basically a zip file. It has a bunch of predefined files in it. Most importantly, Android manifest, which stores anything from permission to components declarations. Of course, you have classes dex, which is the main code, the compiled code of the application. You have, if you're using native libraries, you might have library files in there, maybe multiple files per supported platform. And of course, there's the meta-inf directory, which stores the signature, and it comes from jar signing, which is kind of the basis of APK signing. So when a package is installed, it basically gets split into two parts: code and resources and data. And the code and resources are common for all users. Where they installed is varies slightly by version. In the latest Android M preview 3, it goes into data app, and where example app is the package name. Inside it, you have the native code. You have a file called base ODX, which is the compiled classes dex. If you're using ART, it will be a native code. And of course, you have base APK. Even though the APK is a zip file, it doesn't get exploded on the file system. Basically, all resources and internal data, they are accessed by memory mapping the base APK. And on the other hand, you have data, which is dedicated directories for the apps data. You have, if you have a single user, the application directory will be under data user 0, where 0 is the first owner user. And again, the application package name and different directories for the application's files, databases, and whatnot. If you have multiple users, you will have, actually this should probably will be 10, not 1, because the first secondary user gets the user ID 10, but you will have similar directory structure for other users. And if we look inside into the data directory, what we see is that there are multiple directories, each for the installed application. And the important thing to note here is, which I've tried to highlight, is that each directory has a user, a separate user and group. In this example, this is for the user 0, so you have U0 and A1, A5, and A27 or whatever, which is the application ID. So this effectively achieves part of the application sandboxing, where each application has their own dedicated data directory. And if you look at the permissions in there, you'll see that because the user and the group are the same, the application can access its own files, of course, but it's not available for other applications which are running as a different user and directory. And of course, you have some built-in UIDs like Bluetooth, system, and radio. Well, probably the most important is system, because a lot of services are running as a system user. So it comes up multiple times. Basically, any system service which is running as system they can share files. But of course, if you look at the fourth column, which is the security context, the SE Linux security context of each directory, you can see that besides the user and group, each directory has a dedicated SE Linux type. For user install applications, you can see that it's all up data file, but for system and radio and Bluetooth, it's basically an SE Linux type, which is kind of maps the user those services are executing as like system, radio, etc. We'll go into a bit more detail in the SE Linux part. So package management is actually quite complicated. If you want to look into it, if you have a spare month, you can read through Package Manager Services Java. But Package Manager is kind of the central component, and then you have different installer mount service, media container service, which take care of creating directories, creating encrypted containers, decrypting encrypted application, etc. One interesting fact is that, you probably know it, but you can install application not just going through the ADB install or the package manager. You can also install applications, but just dropping them in the system app and data app directories. And the package manager is monitoring those directories, so it will automatically scan them and install them once they are dropped in there. Not 100% sure how this works on Android M, because I haven't had the chance to try it, but that's how it works on previous versions. So, package management, of course, has a lot more features. One interesting feature is how system apps are updated, because as we said in the beginning, system apps, they live in the system partition, which is read-only. So how do you update them? Do you remount read-only? Do you, whatever you do? So there are different ways to do this. If you update through the Play Store, the system apps are, the updates are installed in the data partition, and the package managers do some internal switching to switch to the newer version. If you update to the OTA file, it's a slightly different story. And of course, you can have a situation where the updated file is with a different signature, so there's a bunch of tricky code that handles this part. Also, Android supports encrypted packages, I believe, since 4.2. Not sure if they are still used that much, but the idea is that for pet applications, the application comes encrypted from the Play Store, and it's end-to-end encrypted to your device. There's also forward looking, which is a basically a DRM system for paid apps. What it does is it installs applications, paid application in an encrypted container. And what it does in addition is it further splits an application into code and public resources. So there is actually 3 parts to our application: the data, code, and public resources. So there's a lot of tricky stuff in there as well. Package verification, something which you may have come across if you see this warning. It's been around since, I believe, ICS 4.0, but it only started being used maybe since 4.2, I believe, and then it's been backported to other versions. But the idea here is that you have verification agents, which basically can stop the installation of a package. So you say install these applications and add this application, and in order to actually install it, you have to get those verification agents, there could be multiple, to agree that it's actually okay to install this application. If you are writing your own Android version or custom ROM, you can of course write your own verification agent. But on most devices, the default agent is maybe nowadays in Google Play services, but originally it was in Google Play Store, integrated into the Google Play Store application. And what it does is basically every time you install an application, an APK, I think the first time you do it, you actually get a dialog which asks you to agree to it, but it analyzes the application, it sends details to Google, like signature, I believe the hash of the classes DEX and hash of the Android XML and maybe other stuff. This is all, of course, changing. So there might be more things in there. And if the Google's database decides that this is a harmful application, you get this dialog. Going on next, code signing is also closely related to application packages. There's 3 main types of code signing. First one is, of course, application packages. APKs, they are signed with X50Q certificates, generally self-signed, but they don't have to be, but actually as Android doesn't really care much. Treated as binary blobs. What it means is that Android doesn't really care what's in the certificate. It doesn't care what extensions it has. It doesn't care what's your name and email address or whatever. So in this sense, code signing is using PKI technologies, but it's not actually PKI. So there's been a lot of confusion about this. What do you do when certificate expires? Do you check for revocation and things like this? Up till now, Android really doesn't care. Another interesting, I think important fact is that because APK code signing, it comes from jar signing. When you say that APK file is signed, it doesn't mean that you have one signature for a particular APK file. What it means is that you have multiple signatures for all the files which are in the APK. The signing certificate is the package identity. It's used for a lot of things, mainly for getting signature permissions and to making sure that an update is coming from the same place as the original file. What else? It's also used for shared user ID, which allows multiple packages to run as the same user and optionally with the same process. Update packages, OTAs, they are also zip files, but they are not using jar signing. Here the signature is over the whole file. It doesn't care what's the actual files inside. And it has been, I don't know, hacked to fit in the zip command. So this is a zip file has like a string command which actually hosts the signature. It's verified by the OS and the recovery image, so it's 2 times. One time when it's downloaded and one time before actually installing it. And one other new thing is that system images may also be signed. This is being like platform dependent or vendor dependent. Now I think it's required, at least the current build system signs it, and the bootloader does check at least the boot partition. A very quick example, if you look in the APK file, there is in the meta-inf directory 2 files. One is shared S, which is the signature manifest, and start RSA is the actual signature. So the signature, the signatures are signatures of the entries in the manifest file. So we have multiple of those, and every one of them can be signed with a different certificate, which has been a problem. Of course, you could have multiple files. You could have 2 classes DEX, which is the basis of the so-called master key exploit. Nowadays, Android uses a so-called strict jar verifier, which makes sure that there are no duplicate files and that all the certificates are actually the same, which is very important for Android because, as we said, the signing certificate is kind of the identity of the package, and when you have many of them, which one is the real one? So it's very important to make sure that all of them are signed with the same certificate. So going on to permissions, there's some academic papers have been published trying to identify what exactly Android permissions are. I don't think that there is any clear consensus, but basically it's an ability to perform a particular operation. Could be regarded as a form of a MAC because it's enforced by implicit kind of system policy. Permissions are enforced at different levels. At the kernel level, which is most interesting, I think, basic, or maybe the only one example is the internet permission, which is the so-called paranoid network security patch to the kernel, which doesn't allow you to use sockets if you're not a member of the internet group. A native service level, which of course native services don't know nothing about permissions, but permissions could be mapped to groups, supplementary group IDs, so they check for those. Framework level, you have dynamic or imperative checking, where the mainly system services, they actually check if the UID calling them over binder has a particular permission. And there is a more declarative or static approach, which everyone is using, is of course services and content providers, they declare what permissions they require in the Android manifest file, and when you try to call them, activity manager and package manager do the actual checking for you. Permissions traditionally have been assigned at install time, of course. The big change in Android 6, there is also runtime assignment and also revocation. Permissions have different protection levels. Those haven't changed much since the beginning. There's the normal, which is basically always granted. There's the dangerous, which previously required user confirmation install time. Now it's at runtime. Signature permissions, of course, require you to be signed with the same certificate as the application that declared the permission. And there's sort of a compromise signature or system, which kind of allows you to get a signature permission if you're signed with the same certificate or you live in the system partition. Nowadays, it's more of a signature or privilege. You have to be a privileged app to get the permission. Of course, we have system permissions. Those are in the Android package, defined in framework, REST, APK. System signature permissions are, if you want to get those, you have to be signed with the platform certificate. Custom permissions defined by applications, they are not so useful because there have been different problems in there, like what's the order of permissions? Can you redefine the permissions? I think the latest version requires you to hold the same signature certificate in order to redefine a permission, but there have been some problems in there. Not 100% sure how it works with Android M. As we said, share ID, where you can run with the same user ID as another package if you sign with the same certificate. The interesting thing here is that all packages part of a shared user ID get all the permissions that have been declared. So if you have application A with permission 1, application B with permission 2, and application C with permission 3, install all of them. Each of them will have permission 1, 2, and 3. And permission groups, they have been there, I believe, also since the beginning, but have been largely underused. They group related permissions and are quite important for Android M. Quick review: install permissions, install time permissions, all permissions granted in install time, dangerous permissions, require user confirmation. So this dialog. No runtime checks required. Once you install an application, you can be sure it has all the permissions you have requested. Cannot be revoked except for some development permissions. Install time permissions are quite fine-grained. There's like lots of them. And if you remember, older version of Android would list all of them in one big list. Another thing, they are granted for all users. So if user 1 updates an application, permissions he grants are also applied to user 2, stored in packages XML, of course. Runtime permission, everybody's talking about this, so just briefly, need to prompt for dangerous permissions, can be revoked at any time. They are granted by permission group, so if you request, for example, the read contacts, the next time you request write contacts, you wouldn't get this dialog because they are in the same permission group. Another important change is that runtime permissions, unlike install time permissions, they are managed per app and per user. So if 2 users install this application, one user can allow the application to use the camera, the other one might deny it. Of course, permissions can be revoked, but some cannot be. This is governed by the device policy, which you can set with device policy manager. So basically, the toggle will be disabled or not shown at all. And next is SE Linux, which is like a huge, huge topic, so we'll just try to go over the basics. SE Linux is it's actually many things. It has many different features, but the way it's used in Android is mostly as a mandatory access control via type enforcement. SE Linux is actually just one of the security modules that can be used in the Linux kernel. It could be, AppArmor and others as well. At the very core, it's quite basic. You have subjects and objects. When a subject tries to access objects, you check the policy to see whether to allow it. A subject is usually a process. An object is a file, socket, whatever. So when you try to access it in the usual discretionary access control, you just look at the permissions. In the case of SE Linux, you go in the kernel to the object manager, security server, and you check the security policy. Once you have a security decision, it's cached for performance. But this is basically what happens. And the most important part, of course, is the security policy. Everything else is just a framework, which always stay the same. A very quick example from the key store policy in Android. This is how policy file looks. Basically, you define a domain for the key store daemon. This init daemon domain is a macro, which basically transitions the key store to this domain when it's first executed. And the bulk of the policy is those allow rules, which basically say that everything which is executes within the key store domain can, in this example, create directories within those directories that have the key store data file type, or for example, connect to the sockets which have the TE type. In Android, it has been modified in a number of ways. Binder support, of course, new init commands, labeling for system properties, which are very important for Android. Labeling for application processes has been extended as well because they have worked from Zygote and domain transition doesn't work as is. We have AC app context file. Middleware map is basically a way to assign labels based on the signing certificate. I think it's getting trimmed down, and in the latest version there's only 2 labels for platform and all the rest. And of course, an alternative view of SE Linux is that a very, very granular policy is not so useful if you can compromise the kernel, which takes care of SE Linux. So some people, of course, think that developer time is better spent hardening the kernel. Multi-user support has been around since 4.2, originally for tablets, now for phones as well. Users are isolated by UID, GUID. Each user gets a system directory and app directory. There's a way that the UID for each application, for each user, is being derived. Another important topic is external storage isolation. External storage is usually, traditionally have been using the VFAT file system, which doesn't have permissions, so there's a lot of bind mounting and Linux namespaces used to isolate external storage. Different type of users. Originally, what Android had is just one user. Primary user owner has full control over the device, similar to root, but of course less control. Secondary users are just additional users, which can be removed by the first user. You can see some of the warnings you get when you set up a secondary user. Restricted profile is a user which shares the application of the primary users, only for tablets. The new stuff since 5.0 are managed profiles, which have separate apps and data, but share the UI with the primary user. It's basically a different persona. For example, your corporate identity versus your private identity. You have guest user, which is temporary user, which can be deleted. We'll get a bit more details about profiles in a bit. Cryptography and SSL, of course, in order to do secure communication and whatnot. You need this stuff. Linux, Android, is based on the JCA provider architecture. It has multiple providers. The interesting ones are the GMS core OpenSSL, which can be dynamically updated via Play services and the Android key store, which allows you to create unextrapolable keys. SSL support is also based on the Java APIs. You have 2 providers. The main one is Android OpenSSL, which uses native code. Certificates and PKI, traditionally Android in the 2.0 and I think 3.0 it's shipped with a hard-coded trust store. Now it's user control. It's managed per user and per profile. And the important thing here is that Android has enhanced certificate chain building. It can use dynamically updated blacklists and pinning. Network security, of course, you support WPA enterprise, different sorts of enterprise. VPNs, important thing for VPN is you can have per user VPNs and per application VPNs. Through the policy, you can require that the data of a particular application goes through a particular VPN. Credential storage is also a related topic. It's a system-managed secure cryptographic store, which allows you to create unexportable keys, so you can generate them and use them, but cannot see the actual key material. The idea is to remain secure even the main OS is compromised. This is, of course, only possible if you have some hardware. backing. It's in the key store system service. There's the HAL interface, which declares the interface for hardware-backed implementation. Typically uses Trustzo. It has, of course, framework APIs, keychain API, key store API, key pair generator, key generator. Key generator is kind of important here because in Android 6 Marshmallow you can actually generate symmetric keys. Another less often discussed thing is online account management. You can get, there's a system store for accounts, passwords, authentication tokens. All of this is managed through the account manager API, which has pluggable architecture, but it's not really so flexible. The interesting thing here is that this is actually kind of one of the first runtime permissions in Android, because you have to agree to use a token, allow this application to use this token per application and per token. Google accounts, of course, are special. Once you initialize the device, you enter the Google password only once, and then it stores a master token. You can control it to the web UI, revoke and add access. Device administration has been in Android since 2.2, I believe, but it hasn't been all that useful. It got a lot of new features in 5.0. It allows you, now the terminology here gets kind of confusing, but the application is called a device administrator. It allows you to send different policies. It needs to be activated by the user and cannot be uninstalled, which is something a lot of malware is using for persistence. Once you agree to this dialog, you cannot uninstall it before first disabling, so a lot of people have no idea that they can disable it. Device administration and policy might be required to sync account data. For example, to get corporate data, you need to activate the administrator first. Android for Work builds on all of this by introducing a work profile, which is as a managed profile which shares the UI with the primary user, but allows for different applications. It follows a predefined profile, separates apps and data, of course. And you can have, as you can see here, the briefcase icon is the Android for Work. Two versions of the same application. You can get the notifications with the same ID. Another thing, related thing is on device owner, which is kind of a super device admin. It can only be installed when the device is first initialized, when it's reset. It has extra privileges and is scoped to the whole device. One thing Android for Work requires is, of course, device encryption, which has been there since 3.0, I believe. It's based on dmcrypt. It's block device encryption, which comes with all the problems and advantages. You cannot have integrity. You encrypt per block. It uses AES with, by default, 128 keys. The actual key is encrypted with another key encryption key derived by the password in 5.0, optionally protected by a hardware key. A different, you can, in 5.0 and beyond, you can encrypt on first boot. And another interesting detail is there is been some support for file-based encryption. Hopefully in the next version we will see this. File-based encryption is interesting because it allows, for example, different users or different applications to encrypt with different keys. Device security, of course, traditionally, lock screen, first only pattern, then PIN and password. Up till Android M, it simply stored the hash of your PIN and password. In Android 6, there is a gatekeeper HAL, which is a hardware abstraction layer for storing and enrolling passwords and PINs, so it can be hardware-backed and more secure if the device supports it. Of course, since 5.0, we have smart lock, which is basically a brand name for trust agents, which are components which, based on some environment factor, they can change the state of the device, locked or unlocked. It's extensible, it's pluggable. What we have, of course, you can write your own if you're using, if you're writing your own Android fork or custom ROM. What we have now is Bluetooth, NFC, face unlock, which are proprietary Google code. Factory reset protection has been there since 5.1, I believe. What it does is saves Google account information on the FRP partition so that you have to enter your password and Google ID after you reset the device. Fingerprint, of course, is the big thing which everybody's talking about, but nobody has seen yet. There's a fingerprint HAL, which allows it to be protected by hardware, if available, of course. Can be used for payment authorization, even though the API there is very confusing, in my opinion. It requires you to create an encryption key tied to authentication. So if you want to see if the user has authenticated in the past 10 minutes, you have to encrypt some data, and if it decrypts successfully, you can assume that they have authenticated. It's probably going to cause many problems for developers. Verified boot is a very important topic. It's basically ensuring the software integrity based on some hardware root of trust. This has been also very device dependent, but finally it's documented, and Android, the latest preview, kind of works according to this state diagram. The simplified boot chain is first you verify the bootloader with the hardware root of trust, then the bootloader verifies the boot partition, and the kernel verifies the system partition. Device or bootloader state can be locked and unlocked, and according to this documentation there, you can use non-OEM keys. So basically, if you have a custom ROM, you can install your own signature keys. Not sure if this works quite yet with the latest preview, but according to the documentation, it does. You have different boot states. If any of the partition is compromised, you get a warning. It works currently for the boot and system partition. You can get a red state. I haven't been able to reproduce the orange state, but probably it also works or will work. DNVerity, it is a transparent integrity checking for block devices, originally used for Chrome OS. It's been integrated in Android since 4.4, I believe, but it's only been deployed recently. What it does is basically it generates read errors if block integrity fails. How it does it is you have the hashes of each block, and then you take hashes of hashes until you arrive at a root hash, which is signed, and it's appended at the end of the partition. Of course, this only works if the partition is read-only, like system, because you cannot build the hash tree like at runtime. In order for all of this to work, one big change that has been introduced in Android is block-based OTA updates. Previously, updates were applied by file, which of course would require you to regenerate the DNVerity after the update and write it down, complicates things a lot. Now it's done in until since 5.0, I think, all updates are block-based, at least on Nexus. Of course, for all of this to work, to be useful, the kernel needs to be trusted because this works inside the kernel. So this is where verified boot comes in. Some changes in 6.0, and basically the biggest change is that all of this is now stateful. So you have two modes, enforcing and logging mode, and the mode is stored in a dedicated metadata partition. The way it works, or it's supposed to work, is first time you boot, if there is a problem with the enforcing mode, you switch to logging mode and show the warning and allow the user to boot. It doesn't it doesn't block the boot completely. So the user has, the choice to either not use the device or use it in a potentially compromised state. And finally, very quickly, NFC, secure elements. NFC has been there for a long time as reader-writer mode, P2P mode, and most importantly, card emulation mode, which has been traditionally implemented with secure element since 4.4, also with host-based card emulation, which basically allows an application to behave like a secure element, which of course is lower security level, but much more flexible. Secure elements, you can have different forms and factors and sizes and whatnot. Of course, the SIM card is a secure element. You can have a micro SD, which includes a secure element. This ASSD standard, I think, is mostly dead, but then again, we have Project Vault from Google, which is also a micro SD card. We might see some development there. Embedded AC, which was, I think, in the original Nexus S, up till Nexus, the next two versions. There are different APIs, restricted telephony APIs, open mobile API, which seeks to unify all of the different supported secure elements, and of course the Android AC, which is just a application which generates APDUs. I think I'm out of time, but this is it. References, official documentation has been updated, very, very worth looking into. There's community wikis and stuff. Of course, mobile security companies publish a lot of interesting stuff. You should look into it. Some recently published books that could be useful. Of course, they are out of date at the point they get published, but still interesting, useful to get the basics, I think. So that's it. Yeah, I should probably look in there.
So I would just like to repeat, if you are wondering, that most of the slides actually have authenticity to back it up with lots more info. It's good for a fellow professors to keep a class of security keys using Porter. Any questions?
Mm-hmm. Yeah. The way it works is there's a required verifier and multiple sufficient verifiers, I think. And the way it's now is the one in Google Play is the required one. So basically, even if you have multiple, if Google Play says okay, it's considered okay. So even if the other ones, now, I haven't looked in the latest code, but I think if you use the Google Play, you cannot override it because it's the required one. If you want to use multiple, you have to use, you have to remove the required one and you have multiple sufficient verifiers in order to have, like, for example, getting data from two sources. If you want to do this, you have to think, I think you have to use multiple verifiers, but remove the Google one because it will override them. Right. Well, I think if you are using like an engineering image, there is a command to disable it. But basically, that's kind of the hard part, because if you get an error, you cannot be sure if this is like an actual compromise or your device is, starting to break, like a physical damage. So there's not really much you can do about it, except go into logging mode and continue using it without, log the errors, similar to SE Linux. Just log the errors, but they keep up coming up. Maybe Nick can get more detail. The question is, DM Verity, of course, you get read errors. If there is a problem, what can you do about it?
So, yeah, one of the challenges with DM Verity is hardware errors occur. One of the challenges with DM Verity is that hardware errors occur on Android devices occasionally. And so the question is, what do we do when a hardware error occurs? Traditionally, before verified boot, the system would continue on. It probably wouldn't even be noticeable by the user. Maybe an image was corrupted, maybe there'd be some small corruption. With verified boot, you have great security properties. You detect that there's a signature failure, and the kernel returns an IO error, and you can't access that. So is returning an IO error sufficient? We're still trying to measure where we're at with verified boot, the level of corruption that we can expect on devices. But over time, I could see it going into a stronger enforcing mode where we actually do return IO errors or even just shut down the device.
Any more questions?
You mentioned something about the Qualcomm Secure OS, right? That you have a parallel OS, the Android, the Linux OS, and the Qualcomm. And you mentioned that you can attack this Qualcomm OS, right?
It's not only Qualcomm, but yeah, it's one of the major.
What is the attack vector for?
There is different stuff. I think there is a talk tomorrow about it, so you can hear more about it. And there is a few recent blog posts that say about it. But basically, I think they have tables they use to jump to code, and you can, through like a kernel vulnerability, you can overwrite those tables, so you can jump to a different place, basically. I can give you the links. There's this guy who wrote like a series of blog posts about the vulnerabilities he discovered. So basically, you go through the kernel and you overwrite some memory, and then. So it's not easy. It's actually quite tricky to get it right, but it is possible.
Thank you.
There is going to be more detail on Trust Zone. Any other questions? Okay, so then let's thank Nikolay again